So this video is about kinetic molecular theory, which sounds like it's going to be an overly complicated topic, but I promise it's not that bad. This is just how we describe our model for the behavior of gases. And a little bit of this is what we talked about in defining an ideal gas. But we're going to expand on that and add a few pieces. So when we are looking at how gases behave, we treat gases like tiny particles that travel in straight lines until they collide with other objects. And so there are three basic assumptions that we make about gases and their behavior. The first, which was one of our criteria for being an ideal gas, is that the particle size is negligible. The second is that the average kinetic energy of the particles in the sample is directly proportional to the temperature in Kelvin. So I want to expand on this a little bit because we know how to calculate kinetic energy, right? Kinetic energy is 1/2 mv squared. It's directly proportional to temperature in Kelvin. So if you have two samples of a gas and they are both at the same temperature, they would have the same average kinetic energy for their particles. Now, if the gases have different identities, they very likely have different masses, which means the velocity will be different relative to the mass so that the average kinetic energy can be the same. So what we find comes out of this, and the fact that you have a mass dependency and a velocity dependency that's related to temperature, what we find is that lighter atoms, well, let's even just say lighter molecules or particles, must move faster to have the same kinetic energy which is directly proportional to the temperature, as heavier atoms, or molecules is what we decided to say, or what I decided to say, and you have to deal with. So mv squared, if the mass goes up, the velocity goes down, and vice versa, if they're at the same temperature. All right. We have one more basic assumption. So we've got particle size is negligible, average kinetic energy is directly proportional to temperature. And then the third one, I think I said out loud but didn't write it down when we were talking about ideal gases, and that is that collisions are elastic. So this means there's no loss of energy when those particles run into each other or into the sides of a container. So I want to do a little bit more about temperature and velocity, and we'll end up defining some additional terms that we use when we're talking about how gases move. So just kind of a restatement of what we just had. At a given temperature, lighter particles travel faster than heavier ones. And I'll draw a picture at the end of all of this that will hopefully illustrate this. And this is all an average, right? So let's specify that. So within a sample, you can have a range of velocities, but on average, you'll have a higher velocity for a lighter particle. And because these individual particles travel within a range of velocities, for the sample, we don't explicitly use v for velocity. We use something called the root mean square velocity, which we say is a u with a sub RMS. Root mean square velocity. And again, this is because there is a range. So the root mean square velocity, URMS, is what it sounds like, the square root of the mean, right, the average squared. And we don't have a way to say, like, find the velocities of the individual particles and then actually calculate this. And I mean, probably someone does, but we as general chemists do not. And I don't expect you to be able to do that. But we do have a way to get into this from some other information. So the average kinetic energy for 1 mole of particles so Ke average is equal to 1/2 times Avogadro's number, because there's a mole of particles, times the mass, times the root mean square velocity squared. And this roughly translates for many particles. There are a couple cases where this doesn't work. Any case I ask you about, this will work. To 3/2 times R times T. And this is showing how kinetic energy is proportional to temperature. So you can connect these in this way. Now, if you need to calculate the root mean square velocity for any practice problems you happen to be doing, the version that's much easier to solve is 3RT over the molar mass, and then take the square root of it. For this equation, you need your temperature in Kelvin. The version of R that you need is 8.314 joules per mole Kelvin. And the molar mass, when you use it, needs to be in kilograms per mole. Okay, so I did promise that I would draw you a picture. I'm going to draw you a picture that shows the variation of velocity with molar mass. So we're going to look at a plot that is at 25 degrees Celsius. So everything is at the same temperature. And we're going to plot the number of molecules versus velocity. So velocity is increasing in this direction. So when we compare things, right, we said lighter molecules move faster. So if we have a molecule that's lighter, I should find that my average velocity is further out to the right. So let's get some different colors. And right, I don't have any numbers on here, so these are all relative to each other. So this first one that I'm going to show you, if I had something heavier than this, it would obviously need to be rescaled. And this plot is for O2, which is about 32 grams per mole. So relative to O2, if I had H2O, which is 18 grams per mole, I should find that it, on average, moves faster than O2. So it might look something like this. H2O, it's about 18 grams per mole. And if I have something even lighter, so H2, it's going to kind of go off my scale that I have here. Dot, dot, dot. Would be going much faster at this temperature, right? Its molar mass is about 2 grams per mole.